Yeah, when they run the test for COVID, they do is they go and they swab, they go up in the nose and nasal passages, and they try to pick up if there are any viruses there, so they grab them on a swab, and then they take that, and those viruses have pieces of RNA in them, which is sort of like DNA, and what they do is they replicate the RNA, they make it copy itself. Just like DNA copies itself, RNA can be copied, and they copy it to the tune of about 1 billion times. And then they run a test on those copies, if they are there, and they say yes or no, the virus is present. And it's all based upon statistical numbers, the whole thing is. And everything that we're doing in school here is based upon statistics. If we wipe down surfaces, we change the probability that somebody who might be positive passes on viral bodies. When we run this filter here, we're filtering out the air more in this room. So what we're doing is we're reducing the probability. The circulation system for the whole building has special filters in it. It's the same kind of filters that they have in hospitals and clinics. They put new ones in this summer. That reduces the probability. You wear a mask. It reduces the probability that if somebody is sick, that it's transpired, it's coming out of their body. So we take all of those numbers and we put them together, and we take all of these different steps that we can take, and that just lowers the chance of passing it on. And if we, in theory, if we could stop passing it on, and we get no new cases, it's gone. It ends. And if you think about it, if nobody is passing the virus on, and the virus only is short-lived, like even on these surfaces, the virus is gone in a couple of days. On a piece of paper, the virus is gone in 3 hours. On a piece of plastic, the virus is gone in 3 days. So if we can do that, if we can stop the transmission and have nobody sick, what are the chances that we're going to have it? 0. It's all theoretical. But it's all based upon models, and they model that with populations and everything. Here's a great one. This is research, and it says this. That's 80%. No, that's not a good 80%. There it is. This is 80%. Maybe that looks the same. But if 80% of the population would wear a mask all of the time, that's 4 out of 5 people. They figure that we can be back to normal in 3 months. End it. That's just 4/5 of the people. So 4/5 of the people would always wear a mask when they're in public, when they're around other people that are not their immediate family. 3 months. Or if everyone would choose to wear a mask 4/5 of the time, the same results. So, I don't know. It seems simple, it's mathematical, but all of this stuff, all of the data that comes out that's real and scientific, it's all based upon math, it's all based upon numbers.
Did you see the thing that the CDC released that 6% of COVID deaths were just COVID and they didn't have underlying conditions? Because I saw that and some people were saying that
6%?
6% of the COVID deaths had no, I wasn't sure. That's what I think it means, but other people were saying only 6% of the deaths were COVID and the other 94 were just other deaths they put in there. Yeah. I think that it was that 6% were just COVID without asthma or the other conditions they already had.
I didn't see it, so I can't comment directly on it.
Something I saw was that they're labeling some deaths as COVID deaths, but they counted a car crash victim as a COVID death.
Where did you see that?
It was, I think, article, I don't know, I forgot the name of it.
You have to be careful what you read, because anybody can write anything, right? You think about wikis, so there's that extreme of it. You can have a wiki site where you just write whatever you want, and anybody can write whatever they want. And that's kind of like what Facebook blog is and things like that. But then there is something called peer-reviewed. And peer-reviewed research reports is what you want to hang your hat on. That's what you want to look at and understand for this type of thing. Because what peer-reviewed means is this. So let's say a couple of doctors get together and they do some research and they say, these are our findings. This is what we found. This is what we believe to be truth. If it's peer-reviewed, that means their peers, other doctors, can review and comment on it. And they can say yes or no. And then what it does is it makes it so that experts with the same level of expertise are critiquing one another. So when you have peer-reviewed research, it's generally considered to be much more reliable because you don't have somebody who is purporting to be an expert, but nobody else can comment on what they are saying is true. And we get ourselves into trouble if somebody just goes and makes a comment. Like if I went and I told you this right here about this 4/5 idea, and I just made it up in my mind, you might believe it. But see, what I did is I went to original research, which is peer-reviewed, which gets put in front, and so a person does the research, it gets put in front of a group of their peers. And their peers have a period of time to be able to review the work, comment on it, and then there's a determination as to whether or not it should be published. And if it's a bunch of bunk, it doesn't get published. Or if it does get published, it has plenty of comments associated with it saying, there's no foundation to these findings, this is not done well. So when we, like when you say that you saw something on CDC, we have to know exactly what they said, first of all. But CDC, essentially everything there that is published has a reference list at the bottom of it. So if you go to any one of their pages and they make statements, at the bottom of the page is all of the references. And those references are original research articles that are peer-reviewed. So that's very scientific. Where if you just go to an opinion page, there's no foundation for what is said to be truth. And unfortunately, that's what's happening with this. There's a lot of both ends of the spectrum going on. And people can be very, very quick to grab something that's startling and shocking and repeat it. But if it's not peer-reviewed, it's not scientific. It's just like storytelling. It can be anything, storytelling of just, made-up stories. So you have to be careful what you read. So what we're doing in the school here, every single thing that we're doing is based upon peer-reviewed research. The filters here, the filtration, the surfaces, the masking, the types of chemicals that we're using, what we're doing to the air as it gets filtered. There's something being added to it that helps to break down viral bodies and bacteria. Those white masks, those have silver and copper in them. Because what silver and copper do is when the virus comes in contact with them, it is very, very quickly disabled. It gets broken apart just by what those chemicals are, what those metals do to things. So that's what we're trying to do in school. So when you say this 6% thing, we've got to see more of what it is. And I'm not even going to comment on it because it'd be speculatory. But if you say, well, there was a car crash death that was classified as COVID, we've got to be careful where we see that being reported and what is their source. And I'm not saying it's true or it's not true. I'm just saying you got to see where it comes from. Is that okay? So this is the kind of stuff that we're doing. We got to get back to this. We got to get this done. Short-lived classes, but we can talk about this stuff more next time we come to if you want. If you dig up the article and email it to me, that'd be cool. Yeah, I mean, if you do, if you don't, I might look for it just for fun anyway, because I do a lot of reading on this stuff. If you can take a pattern and write it out algebraically with variables, that's good. If you can start with a pattern that's written algebraically and then give an example, that's good. If you can do those two things, you have this nailed. You're fine with this lesson. So, did you come up with any of the questions that you were uncertain of when you worked on your homework? No? Do you have your work?
I accidentally forgot it at home.
Okay. So I need to see it, right? Okay. Any questions at all? Or if you look back in the problems that you're working on, did you have any questions? Okay, then we're going to go on. And the next thing is equivalent expressions. And we've done a lot of this kind of stuff. We did it in 7th grade, we did it in 8th grade, and then we did it again at the end of the year in 8th grade. So if you were doing the work that we did in spring and you guys were, we did a lot of this type of thing. Let me scribble away up on the board. Let's see what we can do. Is this thing in your way? Okay. So I'm gonna go to the board. 1-3. Equivalent, that means they're equal to one another. Expressions. We don't have equal signs, so they're just statements. So the examples that they give us have to do with sequences. So a sequence is a number of terms that are put in an order. And kind of the classic one is this right here. If you took 4 toothpicks, you could make 1 square with 4 toothpicks. And then if you added on to that, you started with your 4 toothpicks, and now you want to turn it into 2 squares. You would have to add how many toothpicks?
3.
You'd have to add 3. And then if this sequence here involves the first and the second, and then the third object. The third object gets made a little bit bigger, and it needs how many more toothpicks? 3. 3 more. So what we have here is the 1, 2, and the 3. This is the term number. So it's in this sequence, in this order, it's the item number. So this here is term number. And then the boxes here, these are called the terms. And these terms end up having a count of toothpicks, and that count of toothpicks is the numerical value, or the number value of the term. So what we could do with this is we could say that we can organize it in a table where we have the term number, and then the term given next to one another, sort of like X and Y. But these are different because there's not a 1.5 term number here, or there's not a 2.1 term number. So these are just explicit numbers. And when we graph them with dots. You may remember that. And we don't start with 0 because there's not a 0th term. We either have the first, second, or third, or it doesn't exist. So what we can say is we have 1, 2, and 3. And then our count of the toothpicks ends up being the term. So like you guys said, we add 3 each time. And that's an important part of writing an expression. So if we were going to write an expression for this, here's the shortcut that I think you should use. If you look at the term, this goes up by 3. Then it goes up by 3 again. So we can see that pattern sticks. That adding of 3 sticks. So then if you had a 4th term, you'd still add 3 more. You'd have a total of 13. So if you can see that this happens a couple of times in a row, the same amount is being added. Here's the trick. First of all, we're going to look at the term and how it either increases or decreases. And that's what we wrote here, that +3, +3, +3. If it goes down, you just say it goes -3, -3, or whatever amount. Then, the second step is to use that number and multiply it by the variable n. So we're going to take that increase, so that's a +3 multiplied by n. And then we're either going to add or subtract something to get the t value. So after you do this, writing this basic idea out, this basic pattern, you go back and you check. So you check to find what you either add or you subtract to get t. So what I mean by that is 3 times the n. So 3 times 1 is 3. So what do you have to do to make it equal to 4? 3 times 1 and then plus 1. And then let's look at the second one. So now we're going to take 3 times the 2, which is the n value here, and 3 times 2 plus 1 should equal 7, and it does. So we just confirm that it works. And then what we have here is the expression, together with the equal sign as an equation. But right now we're just looking for expressions. So to continue on and keep all of your work organized, if we went here and we said, well, for any n value, the rule to find t is going to be this right here, 3n plus 1. So every one of these numbers here is 3n plus 1. Here it's 3 times the 4 plus the 1. There it's 3 times the 3 plus 1, making 10. So oftentimes what they'll ask us to do is find the 100th term. Well, 100 is now n. So that's going to be 3 times 100 plus 1. There's 301. There's your 100th term. This would be the nth term. So we're just talking algebraically. The nth term, and you can substitute any number you want for nth. But the nth term is 3n plus 1. That's how the language works with that. So the first term is 3 times 1 plus 1. The 80th term is 3 times 80 plus 1, and so on. Is that okay? And take a look at this one. Dots. So the dots, well, I'm not sure what page that is. It looks like it's 21. So 21, there you go with the dots. If you were going to make a table of n and t, this is your n value, and this, the count of dots is your t value. So in the first term, how many dots? In the second term? In the third term? 11. Okay. So, push this all the way over. I don't know if it's gonna show. Yeah, it kinda does. So I made a table with 1, 7, 2, 9, and 3, 11. So how does this change? Goes up by 2. Up by 2. So then, if this is n, to find t, I would have to take 2 times n. And then do you add or subtract so that it works? How much do you add? So in other words, for this one right here, this would be 2 times 1. And what do I have to do? That's not very good. What do I have to do to get 7 after I multiply 2 times 1? Plus 5. And then here, 2 times 2 plus 5, will that equal 9? Yes, no, maybe? Does that work? So down here, 2n plus 5, that's the expression to model that pattern, that sequence. So if you can do that, and then plug in like 10 or 20 to find the 20th term or the 10th term, you'll be good to go. Okay, so then here's the other part of this lesson. So in the first example, they give us 2 expressions, and we want to find out if they're equal to one another. So when you're doing this type of work, if you begin with the table like they have it in the book, I would suggest that. In order to be showing your work appropriately, you're going to have to give me the numbers instead of just saying yes or no, they are or are not equivalent. So in this case here, they give us n values of 1, 2, 3, 10, 20, 35. Might be a little excessive. You don't have to do absolutely all of them, but we'll take a look. And then they say ALF says that this is the relationship for a pattern. Oops. And then the other person, Beth, says that this is the relationship. And the question is, are they one and the same? So we're not going to combine like terms algebraically. We're just going to show that we can do this work with a table. Later on, we'll take a look how we can combine like terms and such. So if we just substitute 1 into here, you get 1 plus 1 plus 3 plus 1 plus 1. What does that equal? Seven, yeah. Not rocket science, addition. Here, we have 5 plus, and then the n value of 2. 2 times 1, what does that equal? 7. So it appears they're the same. But using numbers like 0 and 1 to prove something is the same is not safe. There are a lot of instances where they look like they're the same, but they're not, just because you used unusual numbers like 1 and 0. So what we got to do is try a couple of times here. So I'm just going to plug away. 2 plus 1 plus 3. 2 plus 1. How much do we have then? Nine. Come over to the other expression. How's that one shake out? What is that going to equal? That's 9 also. So we probably have the same expression going on, just written differently. Try one last time. If we substitute 3 for 9, we get 11. And on the other, we get 11. So they're same. So Now, they just give us more numbers to check with, but I'll tell you this, in practice, if you can come up with 1, 2, and 3 as your inputs and you get the same output, you have the same expression, no question. So I'm not gonna fill these in for the sake of time, but I think you get the idea, and we've done this kind of stuff quite a bit. So we're reviewing, we're taking a look back. Okay, last example. The last example brings in this idea of something called a counterexample, which I know that we hit on lightly last year, but it comes up again and again in math. A counterexample is an instance or an example where you maybe plug in values into the variable, and it shows that something is not equal to something else. So they give us example number 2. Azami and Haley write expressions to describe some pattern that they're looking at. And the one kid writes k subtract 8 plus 5. They say that's what the pattern is, that's what's going on. And then the other kid says, well, it's k minus 13. Now they're not looking at one another's work, they're just looking at some pattern. So this is how one kid comes up with it, that's how the other comes up with it. And all we want to know is, are these two expressions equal to one another? So if I put an equal sign in between them, and then I substitute numbers, so here's what we could do to show your work. Here's some k values, 0, 1, 2, 3. We want to find out if we substitute 0 in for this, 0 in for this, are they equal? So what is 0 minus 13? How much?
Negative 13.
Negative 13. Is this equal to negative 13?
No.
No. 0 minus 8 is negative 8, follow order of operations, plus 5?
Negative 3.
Negative 3. Not equal. That then becomes a counterexample because it proved that they are not equal. So the kids are saying these are equal, and then all I got to do is use this and say, here's one counterexample that shows they are not equal. Now, if you found it was still equal, you can't just then say that the expressions are equal to each other. You have to go through a few examples. And you have to avoid using 0 and 1. So you'd have to use maybe 0, 1, and 2, and then find out if they are indeed equal or not. But you have to do it with several values. So for the sake of time, I'm not going to fill all of those in either, like they were kind of expecting us to do here, but this works. Any one of these numbers, it's not going to hold true that they would be equal. Therefore, any one of those numbers could be used as a counterexample. So the way you could answer this is a counterexample is k equals 0 because it shows that they are not equivalent. That's it. So there's your homework. In that first one there, I think that the number of squares, so don't be misled thinking it's toothpicks, but it's the number of squares that they're looking for your t value or your term